Welcome to Sleepy Astronomy. I'm so glad you've joined me tonight. Let your thoughts grow quiet and your breathing slow, as if you're floating weightlessly between the stars. Far beyond our skies lie dozens of hidden worlds, circling the planets, each with its own strange beauty and quiet secrets. Tonight, we'll drift among them, exploring the mysterious moons of our solar system. In the shadow of planets and in the silence between the stars, there are moons, companions to worlds both vast and small. Natural satellites circle their primaries in rhythms shaped by time, gravity, and ancient violence. Our solar system is home to more than 200 known moons, scattered from the scorched skies near the Sun to the icy darkness beyond Neptune. They vary from rocky fragments to vast spheres shrouded in thick atmospheres, each shaped by circumstances both familiar and strange. Scientists have long sought to understand how these companions came into being. Theories suggest three main pathways to the formation of moons: co-formation, capture, and the mighty violence of a giant impact. The co-formation theory proposes that moons form alongside their planets, from the same disk of gas and dust that surrounded the young stars. In this model, just as the planets condensed out of the protoplanetary disk, smaller clumps of matter nearby coalesced into moons. These are often called regular moons. They tend to orbit close to their planet, following near-circular paths above the equator, traveling in the same direction as the planet's rotation. Jupiter's large moons fit this model well. They formed in place, embedded deep in the planet's gravitational influence, orbiting with calm precision. But not all moons are so neatly ordered. Some appear to have been captured by chance. When a wandering asteroid or minor planet ventures too near a massive planet, it can be snared by gravity. These captured moons are labeled irregular because they often have highly elliptical or tilted orbits. Some even orbit backward against the spin of their planet. Neptune's moon Triton is thought to be one such rogue, a captured object now locked in a slow spiral toward its host. Perhaps most dramatic of all is the giant impact hypothesis. This model suggests that a planet can form a moon after a colossal collision, one so powerful that it tears both bodies apart. The debris, blasted into orbit, eventually cools and clumps into a satellite. This is the leading explanation for the origin of our own moon. Billions of years ago, Earth is believed to have been struck by an object the size of Mars. The impact reshaped both bodies, and in the fiery aftermath, our moon was born. Once formed, moons begin their long dance around their planets. They shape and are shaped by the systems they inhabit. Some help to stabilize a planet's tilt, creating predictable seasons. Others affect the dynamics of surrounding rings, or influence the orbits of nearby moons. A large moon can help protect its planet from impacts, or sweep up debris from space, acting almost like a cosmic guardian. The difference between regular and irregular moons lies not just in their paths, but in their stories. Regular moons tend to be large and round, with stable relationships to their planets. They suggest quiet formation, order, and ancient coexistence. Irregular moons speak of past chaos and capture, of objects from faraway regions that now orbit in uneasy truce. Together, moons add depth and complexity to planetary systems. They offer clues to a planet's past and forecasts of its future. Some hide vast oceans beneath icy crusts. Others are riven with volcanoes or covered in impact scars older than most planets. As we send our spacecraft into the solar system, these moons rise in importance, not mere afterthoughts, but worlds in their own right. In their silence, they watch their planets turn. From the inner solar system to the edges of the sun's domain, moons remind us that the story of planets does not end with the planet itself. It reaches outward into the embrace of gravity and the hidden histories traced in every circle they draw through the dark. We call it the moon. It has no other name, though we now know tens of moons orbit other worlds across the solar system. Its presence in Earth's sky has shaped the rhythms of our planet since before life began. And yet, the moon tells a story of violence and cosmic chance. Around 4.5 billion years ago, Earth was young, still forming. Into this chaotic world came a planet-sized object, something Mars-sized, possibly named Theia. It struck Earth at a glancing angle. The impact was catastrophic beyond imagination, melting both bodies and throwing debris into space. From this glowing debris, caught by Earth's gravity, the moon began to form. This is the giant impact hypothesis, the explanation that best fits the evidence. The moon's composition is similar to Earth's outer layers. It lacks the dense metal core Earth possesses, suggesting the debris came mostly from the crust and mantle. Over time, gravity drew the orbiting matter together. In weeks to months, the moon began to coalesce, glowing from its own internal heat, its face still molten. It was born hot, bathed in the light of a young and violent sun. Today, the moon is airless and silent, roughly 1/4 the diameter of Earth and about 1/80th the mass. Its gravity is too weak to hold an atmosphere. Meteoroids, left unchallenged by air resistance, strike the surface and leave their marks. Vast plains of solidified lava, called maria, record ancient volcanic activity. The highlands, older and lighter in color, carry scars from a time of incessant bombardment. We see the moon's face from Earth, always the same side, because it is tidally locked. Its rotation matches its orbital period, so one hemisphere always looks toward us, while the other, the far side, remained unseen until spacecraft were sent to glimpse it. This regularity gives rise to the lunar phases. As the moon orbits Earth every 29.5 days, sunlight illuminates it from varying angles. We see crescents, half-moons, and full moons in a cycle as old as time itself. Occasionally, the moon aligns precisely between Earth and the sun, casting its shadow across our planet. These are solar eclipses, brief moments when day becomes night, and the sky reminds us of cosmic mechanics at work. At other times, Earth passes between the moon and the sun. Our shadow darkens the moon's surface in a lunar eclipse, turning it an eerie red, as only the longest wavelengths of sunlight scatter through Earth's atmosphere and reach it. The moon affects us more directly too. Its gravity tugs at Earth's oceans, causing the tides. Though the sun also plays a role, the moon's proximity makes its influence greater. This tidal interaction also slows Earth's rotation gradually, lengthening our days over geological time. It keeps Earth's spin axis stable, reducing chaotic swings that might otherwise disrupt climate. Without the moon, life as we know it might not exist. Humans have long looked upward, imagining stories on the moon's face. But in the 20th century, imagination turned to action. In July 1969, Apollo 11 carried Neil Armstrong and Buzz Aldrin to the moon's surface, while Michael Collins orbited above. For the first time, conscious beings stood upon another world. Between 1969 and 1972, 6 Apollo missions landed, collecting rocks, deploying instruments, and bringing back knowledge that transformed our understanding. After Apollo, human missions ceased, but robotic explorers continued. Lunar orbiters mapped the surface, landers studied the soil. Now, a new era dawns. The Artemis program, led by NASA and international partners, plans to return humans to the moon. This time with new goals: scientific exploration, scientific discovery, and use of the moon as a gateway to deeper space. The moon remains close, yet still filled with mystery. It is a relic of early solar system history, a stabilizing companion, a silent witness to Earth's story. And it is a destination once again. Mars has 2 small moons, Phobos and Deimos. They are unlike our own moon. These companions are tiny, irregular in shape, and scarred by impact craters. From the surface of Mars, they appear faint and strange, more like asteroids drifting too close than traditional moons. And that may be precisely what they are. Most likely, they came from the outer regions of the asteroid belt. Their dark, carbon-rich surfaces resemble C-type asteroids found there. Their low densities suggest a loose, porous composition, more like rubble piles than solid rock. If they formed with Mars, we would expect more regular shapes, stable orbits, and denser material. But this is not what we see. Their orbits add to the mystery. Deimos orbits far from Mars in a nearly circular path, taking about 30 hours to complete one revolution. Phobos, on the other hand, hugs the planet closely. It spins around Mars in just under 8 hours, faster than the planet rotates. As a result, it rises in the west and sets in the east, appearing to race across the sky. Phobos is doomed. Because it orbits so close, tidal forces between it and Mars are gradually pulling it inward. Each century, it descends roughly 2 meters closer to the Martian surface. At this rate, it will either crash into Mars or break apart into a ring of debris within the next 30 to 50 million years. On cosmic timescales, that is the blink of an eye. Its surface bears the evidence of its troubled path. One feature, Stickney crater, is a massive impact scar compared to Phobos's overall size. The shock of that impact nearly shattered the moon, and the fractures from that event still thread across its surface. Deimos, smaller and more distant, lives a quieter existence. Its orbit is slowly growing, lifting it higher with each passing millennia. Unlike Phobos, it may escape Mars's gravity completely billions of years from now, sailing alone into the void. Yet despite their small size, both moons attract human interest. Their low gravity and proximity to Mars make them potential stepping stones in future exploration. Landing on Phobos or Deimos would require far less fuel than descending to the Martian surface. Astronauts could use them as observation posts or fuel depots, bringing us closer to the red planet with minimal cost. Phobos, in particular, has drawn attention for its potential role in colonization efforts. Artificial structures could be anchored to its surface. Supplies could be stored there, awaiting missions to and from Mars. Even telescopes and communication arrays could be placed on its more stable slopes, protected from the planet's dust storms and thermal extremes. For scientists, these moons are also records of deep time. They may preserve clues about the early asteroid belt and Mars's ancient gravitational balance. Understanding how they came to be and what forces have sculpted them teaches us not only about Mars, but about the nature of planetary capture and orbital evolution throughout the solar system. In their quiet, eerie drift above Mars, Phobos and Deimos tell a story, not of grandeur like Saturn's rings or Jupiter's vast moon systems, but of cosmic luck and ancient forces at play. They are fragments from elsewhere, now bound to a world that might one day be our own. They remind us that even the smallest objects in the sky can shape human dreams. In time, we may leave footprints on their dark, dusty surfaces. And when we do, those first steps will mark the edge of a new chapter, where humans venture into the Martian system, not only to visit, but to stay. The 4 largest moons of Jupiter are so distinctive and fascinating that they stand apart even in a solar system filled with wonders. Known as the Galilean moons, they were first seen by Galileo Galilei through a modest telescope in the year 1610. They orbit the gas giant in perfect mathematical rhythm, locked in a gravitational dance that has lasted for billions of years. Each one is a world of its own, shaped by forces both furious and gentle, ancient and ongoing. Io lies closest to Jupiter. Its surface is a palette of yellow, orange, and white, stained by sulfur compounds from countless volcanoes. In fact, Io is the most volcanically active body in the solar system. These eruptions are powered not by internal heat alone, but by friction. As Io orbits, it is stretched and compressed rhythmically by Jupiter's immense gravity, as well as by the gravitational tugs of its neighboring moons. This tidal heating generates enough energy to melt rock beneath the surface, feeding deep reservoirs of magma that rise and explode onto the surface. The result is a constantly changing world, where plains are covered and recovered in lava, and mountains rise and crumble within geological heartbeats. Europa is next in line, and its surface tells a very different story. It is smooth and bright, laced with reddish streaks that trace across a surface of water ice. But beneath this icy shell lies something remarkable: a global ocean kept liquid by the same tidal forces that heat Io. This ocean could be as deep as 100 kilometers, containing more than twice the volume of all Earth's oceans combined. Cracks and ridges on the surface suggest that the ice shifts over time, possibly interacting with the warmer waters below. Some areas may even experience cryovolcanic activity, where plumes of water burst upward and freeze. These ingredients, liquid water, chemical nutrients from the rocky seafloor, and a source of energy, make Europa one of the most promising places to search for life beyond Earth. Ganymede is the 3rd Galilean moon, and the largest moon in the solar system, even bigger than the planet Mercury. It holds a complex interior, an iron-rich core, a rocky mantle, and a crust of water ice. Like Europa, Ganymede also likely hides a subsurface ocean, though its depth and nature are still uncertain. But Ganymede is unique among moons in another way. It has its own magnetic field. This indicates a partially liquid, rotating core, and creates auroras, rippling patterns of light, in the moon's thin atmosphere. Its surface is a mix of darker, older terrain, and lighter regions marked by grooves and ridges, evidence of tectonic activity in the past. Ganymede is a quiet giant, preserving clues to how moons form, evolve, and sustain themselves across billions of years. The outermost of the Galilean group is Callisto. In contrast to its siblings, Callisto bears the scars of an ancient, static world. Its surface is saturated with craters, some overlapping and forming enormous multi-ringed structures. The largest, Valhalla, stretches out for over 4,000 kilometers. Unlike Io or Europa, Callisto shows no signs of eternal heating. It has evaded the tidal stresses that shape the inner moons, existing in a near-perfect gravitational balance beyond the resonance. And yet, beneath its battered crust, there may still be a slushy layer of water mixed with salts, hinting at a hidden story. In its bleak silence, Callisto preserves a memory of the early solar system, a time when bombardment was fierce and unrelenting. These 4 moons, Io, Europa, Ganymede, and Callisto offer a condensed glimpse into nearly every planetary process known to science: volcanism, tectonics, magnetism, and the potential for oceans and life. They orbit together in a delicate clockwork motion, each influencing the others through gravity and syncopated resonance. Their diversity is not random, but born of their distance from Jupiter, their composition, and their intertwining histories. In their shadows and light, frozen plains and fiery pits, we glimpse not only the mechanics of celestial bodies, but the possibility that far from Earth, beneath layers of ice or within molten chambers, other forms of nature may stir. Beyond the 4 great Galilean moons, Jupiter is home to a rich and complex family of smaller, lesser-known satellites. Over 90 moons orbit this gas giant in total, and many of them defy expectations. These moons are diverse in size, shape, and motion, carving out unusual and sometimes chaotic paths through Jupiter's vast gravitational domain. Some of these moons belong to what astronomers call the Amalthea group. These inner satellites orbit very close to Jupiter, tightly bound and small. They include names like Amalthea, Phoebe, Adrastea, and Metis. Unlike the Galilean moons, which follow nearly circular and well-aligned orbits, these inner moons move quickly around Jupiter, trapped between the planet's powerful gravity and the inner edge of its ring system. Amalthea, the largest of this group, is irregularly shaped and reddish in color. Its oddly asymmetrical body suggests that it was not formed by slow accretion around Jupiter. Instead, it may be a captured remnant from elsewhere in the solar system. Its low density hints at a porous, icy composition, and some scientists believe Amalthea may be more rubble heap than solid rock. Farther out, Jupiter's sky becomes increasingly crowded and bizarre. Here, we find the irregular moons. These are typically small, misshapen, and follow eccentric orbits, many of them retrograde, meaning they orbit in the opposite direction of Jupiter's spin. It is highly unlikely that they formed in place. Rather, they were almost certainly captured from beyond the Jovian system. Their chaotic paths reflect both their distant origins and the tumultuous journeys that brought them here. One of the largest of the irregular moons is Himalaya. It leads a group of moons that all share similar inclinations and distances from Jupiter. Unlike the chaotic orbits of some others, Himalaya's path is relatively stable, and scientists believe it may be the shattered remnant of a larger body, broken apart in ancient collisions. Even farther out lies Pasiphae, namesake of another family of irregular moons. These satellites are darker, more eccentric, and more inclined than those in the Himalaya group. Pasiphae itself is retrograde. Its backward orbit, along with its size and distance from Jupiter, tells a story of violent origins. Perhaps Pasiphae was once an asteroid, captured by Jupiter's gravity, and eventually fragmented into a loose collection of related moons. These siblings now wander the far reaches of Jupiter's kingdom in slow, looping trajectories. Such captured moons offer a window into the dynamic past of the outer solar system. Their arrival was likely messy. To be caught by Jupiter, an object must lose speed, perhaps by crashing into another body, brushing against a gas-rich disk, or being tugged by third gravitational force. The process leaves behind orbits that are tilted, stretched, and unstable. Some of these captured moons may not stay bound forever. Over millions of years, gravitational tugs from the Sun and other planets may eject them into the dark once more. Each of these lesser moons plays a role in shaping the environment around Jupiter. Some contribute dust to the planet's faint ring system. Others influence one another through gravitational nudges, like a subtle dance marked by distant encounters. The irregular moons, though small, help explain how the Jovian system grew and evolved, hinting at a time when the outer solar system was a chaotic realm of wandering rocks and shifting gravities. It is easy to overlook these minor moons in the shadow of giants like Europa or Ganymede, but in their irregularity lies a deeper story, one of chance, collision, and gravitational capture. They are survivors of ancient journeys, fragments of disruption, frozen in time. Together they remind us that even in the immense machinery of the solar system, the smallest members carry the fingerprints of its restless early days. Saturn, the jewel of our solar system, is encircled by an empire of moons. Among them, two stand apart, Titan and Enceladus, worlds as different as they are remarkable. One thick with atmosphere and mystery, the other gleaming beneath a shell of ice, hiding a secret ocean that may cradle the seeds of life. Titan is Saturn's largest moon, even bigger than Mercury. Wrapped in a dense atmosphere rich in nitrogen, it is alone among moons in that regard. The veil is thick and orange, cloaking the surface from view in visible light. But beneath it, we've discovered a world carved by methane rain, sculpted by wind, and patterned with vast lakes and seas of liquid hydrocarbons. It is strange and alien, yet hauntingly familiar. Radar maps from the Cassini spacecraft revealed river channels that meandered toward dark, smooth lakes. At the poles, seas bigger than Earth's Great Lakes lie quiet, rippling beneath a sky of eternal twilight. Complex clouds form, driven by seasons that last over 7 years each. Rain falls, not of water, but of methane and ethane, cycling in a system uncannily like Earth's water cycle. Here, for the first time, we found weather systems on a solid surface beyond Earth. The dunes of Titan stretch across equatorial regions, shaped by wind and interrupted by ice mountains. The icy crust hides an internal ocean, water mixed with ammonia, perhaps, locked beneath a surface tens of kilometers deep. That makes Titan more than a frozen curiosity. It is a planet-like world, with chemistry that could hint at life's potential in places we once thought barren. Farther out orbits Enceladus, much smaller than Titan, only about 500 kilometers wide, and with a bright, icy surface that reflects nearly all sunlight. At first glance, it might seem like just another frozen moon, but from its south pole, something extraordinary happens. Jets of vapor and ice erupt into space from fractures in the crust. Tiger stripes, as we've come to call them. When Cassini flew through those plumes, it tasted a hidden sea. In the ice grains and vapor, scientists found salt, organic compounds, and even molecular hydrogen. That last clue is crucial. Hydrogen, in contact with warm rock in the ocean's depths, could provide energy for life through chemical reactions similar to those found near Earth's deep-sea vents. And so, what once seemed an inert ice ball became one of the most promising places in the solar system to host life. Not because it resembles Earth in appearance, but because it has water, energy, and the chemistry that life requires, all beneath just a few kilometers of ice. The implications are profound. Titan shows how organic chemistry can evolve in unexpected environments. It could even support life based on unfamiliar biochemistries, driven by liquid methane rather than water. Enceladus offers an ocean world whose ingredients are within reach. Its geysers deliver samples directly to space. We don't yet know what swims within, if anything, but we have reason to search. The Cassini spacecraft orbited Saturn for more than a decade, a quiet sentinel among the moons. Its dying dive into the planet's atmosphere in 2017 was deliberate. a measure to protect possible life on moons like Enceladus from contamination by Earth. Cassini revealed that these moons are not footnotes to Saturn's grandeur. They are active worlds, dynamic and alive in their own way. Titan, with clouds and lakes, may help us understand the earliest days of Earth. Enceladus, a gleaming ocean world with jets powered by warmth from its core, challenges our assumptions about where life can exist. These are not barren rocks. They are laboratories of nature, sculpted over billions of years. They offer clues to the origins of life and the processes that shape planets. In their icy shells and thick shrouds lie the dormant stories of past and possible futures, waiting for us to read them with the next generation of explorers. Beyond Titan and Enceladus, Saturn is host to a rich and varied family of moons, more than 80 known to date. These moons range in size from small, irregular fragments only a few kilometers across to world-sized bodies carved with ancient canyons and bright cliffs of ice. Some orbit in neat, undisturbed paths, while others dance through the outer reaches of Saturn's gravity in eccentric, inclined orbits. Among them are objects that defy simple classification, striking, enigmatic witnesses to the ancient processes that shaped the solar system. Mimas is one of the more curious members of this family. Though only 400 kilometers wide, its most recognizable feature is a vast impact crater known as Herschel. This depression spans almost a third of the moon's diameter, with steep walls and a central peak that rises like a mountain from its heart. The resemblance to the fictional Death Star from Star Wars is uncanny, but Mimas is entirely natural, scarred by an ancient collision that nearly shattered it. Despite its appearance, Mimas is quiet and cold, a frozen remnant with a surface composed mostly of water ice. Tethys orbits closer to Saturn, a pale and heavily cratered world of ice, slightly larger than Mimas. One feature dominates its terrain: Ithaca Chasma, a canyon system that runs over 1,000 kilometers in length, almost 3/4 of the moon's circumference. It might have formed when Tethys froze solid early in its history, expanding slightly and cracking open like a frozen fruit. Like many of the inner moons, Tethys maintains a locked, synchronous rotation, always showing the same face towards Saturn in an elegant rhythm shaped by gravity over aeons. Then there is Dione, slightly larger still and orbiting farther out. Dione shares a kinship with Tethys in composition, water ice with small amounts of rock, but its surface tells a more complex story. On one hemisphere lie bright, wispy streaks, curved and broken lines that cross over craters and plains in ghostly pattern. Once thought to be frost deposits, these streaks are now understood as icy cliffs, exposed by tectonic fractures in the crust. Beneath the icy shell, some evidence suggests a possible liquid ocean may exist, kept warm by tidal forces that still echo faintly through Dione's interior. Rhea, another icy moon, is the second largest of Saturn's satellites after Titan. Though similar in composition to Dione, Rhea has a pitted, ancient surface and a sense of timelessness. Crater upon crater tells the tale of billions of years adrift in Saturn's orbit. Intriguingly, Rhea might have a thin atmosphere composed of oxygen and carbon dioxide, extremely rare for a moon of its kind. If confirmed, it would suggest chemical interactions between surface ice and energetic particles from Saturn's magnetic field, hinting at unseen dynamics even on a seemingly inert world. Among the more irregular members is Hyperion, a small, potato-shaped moon with a rotation that defies predictability. Instead of spinning smoothly, Hyperion tumbles chaotically through space, its motion influenced by its elongated shape and interactions with larger neighboring moons. Its surface resembles a sponge, low in density and full of voids, covered in strange dark material that collects in its many craters. Hyperion challenges our understanding of how small bodies evolve under the subtle pressures of time and gravity. Iapetus is perhaps the most enigmatic of all. Merely 1,500 kilometers across, it holds a prime orbit far from Saturn's ring system. One hemisphere is bright as snow, while the other is 10 times darker, dark enough to absorb most sunlight. This dramatic contrast, known as albedo dichotomy, is likely due to a mixture of thermal effects and material from other moons coating Iapetus's leading face as it moves through space. Even stranger is the equatorial ridge, a raised line of mountains that runs like a seam around the moon's middle. Its origin remains uncertain, evoking images of ancient processes now lost to time. Together, these moons tell stories of ancient impacts, tidal shaping, and curious geology. Frozen plains and fractured cliffs speak of past stresses and silent movements beneath icy crusts. Their diversity reveals the complexity of Saturn's gravitational reach and the many ways small worlds survive, evolve, and remain connected within a wider planetary system. Saturn's other moons may lie in the shadows of Titan and Enceladus, but in quiet ways, they too offer glimpses into the deeper history of our solar system. Uranus, the seventh planet from the Sun, orbits on its side. Its axis is tilted by a staggering 98 degrees. This means that for part of its long 84-year journey around the Sun, Uranus points one of its poles directly at the star. Its seasons are unlike anything we see on Earth. The same peculiarity extends to its moons, 27 of them, each caught in this skewed, elegant dance. Many of these moons are named after characters from the works of Shakespeare and Alexander Pope, a touch of poetry drifting far from Earth. Among them, 5 are considered major: Miranda, Ariel, Umbriel, Titania, and Oberon. They are icy worlds, orbiting within a complex and tilted system. Because Uranus rotates almost perpendicular to its orbit, its moons follow equally skewed paths, moving in orbits that appear vertical compared to the rest of the solar system. Miranda is perhaps the most fascinating of them all. Only about 500 kilometers across, it is small, but its surface tells a story filled with violence and upheaval. Giant canyons carve into its face, some 20 times deeper than the Grand Canyon. Strange patterns of ridges and troughs stretch across its icy crust. These features suggest tectonic forces, perhaps driven by tidal heating in Miranda's past. Some scientists believe it was shattered by a massive impact and later reassembled under the pull of its own gravity, giving it a patchwork appearance, like a world stitched back together. Ariel is brighter than the other moons. It shows evidence of resurfacing events, with fewer craters and smooth plains, suggesting that internal activity may have reshaped its surface within the past few billion years. Gigantic rift valleys stretch for hundreds of kilometers across its landscape. Like Miranda, Ariel may have had a warmer core at one time, or perhaps tidal forces triggered motion beneath its icy shell. Umbriel lies in contrast. It is darker than its neighbors and appears more ancient and preserved. Its surface is marked by impact craters, telling the story of a world that has been still for ages. Yet, even here, surprises exist. A bright ring of material surrounds one large crater, a splash of light on an otherwise shadowed surface. Titania, the largest moon of Uranus, is merely 1,600 kilometers wide. It has both old cratered terrains and long fault valleys, some stretching across thousands of kilometers. These features suggest that Titania once expanded from within. Perhaps liquid water froze in its interior, cracked the crust, and forced the moon to grow. Opposite in name but similar in size is Oberon. Dark and heavily cratered, it sits farthest from Uranus among the major moons. Some of its craters contain mysterious white deposits, possibly water ice exposed by impacts. All 5 of these moons orbit Uranus in the same strange plane, tipped over just like their planet. And most orbit in the same direction Uranus spins, known as prograde motion. But some of the smaller, more distant moons defy this pattern. They follow retrograde orbits, moving in the opposite direction to the planet's spin. These irregulars are likely captured objects, once wandering the solar system until they were caught by Uranus's gravity. The entire Uranian system is veiled in an atmosphere of mystery. Voyager 2 is the only spacecraft to have visited, sweeping past in January 1986. In a few hours, it revealed breathtaking detail. Canyons on Miranda, the clean brightness of Ariel, the still hush of Umbriel, and the sprawling terrain of Titania and Oberon. But many questions remain. What lies beneath their surfaces? Are there oceans hidden beneath the ice? Have they ever supported the conditions necessary for life? As Uranus sails on its tilted journey through the distant reaches of the solar system, its moons continue their slow orbits. Silent and cold, they are frozen time capsules of the early solar system, shaped by their unique gravitational ballet. They whisper of ancient geologies and unseen interiors, waiting for the day we return to learn their secrets. Triton is unlike any other major moon in the solar system. Cold, distant, and mysterious, it moves in the opposite direction to Neptune's rotation. This retrograde orbit is more than just a curiosity. It's a clue to Triton's past. Most large moons orbit their planets in the same direction the planet spins. This is the result of co-formation, when moons form alongside their planets from the same swirling disk of dust and gas. But Triton's backward path suggests it was not born in orbit around Neptune. It was captured. Scientists believe Triton was once a free-floating object in the outer solar system, possibly part of a binary pair. Long ago, as it drifted near Neptune, a chance encounter changed everything. Some theories propose that the gravitational interaction between Neptune and Triton, and possibly a partner Triton once had, ripped Triton from its path and locked it into orbit. That event would have released immense energy. The original orbit would have been wildly elliptical, but over time, it settled into the almost circular motion we observe today, albeit backwards, a lasting testament to its dramatic origin. Triton's surface tells us it is still active. NASA's Voyager 2 spacecraft, during its fleeting encounter in 1989, revealed a landscape of frozen plains, ridges, and dark streaks that suggest recent change. Among the most striking discoveries were signs of cryovolcanism, ice volcanoes. These formations appear to spew material not of molten rock, but of water, ammonia, or methane in liquid form. When this material reaches the frozen surface, it instantly solidifies, creating smooth plains and remolded terrains. Perhaps even more profound is the possibility that a subsurface ocean lies beneath Triton's icy shell. Heat generated by tidal forces, gravitational tugs from Neptune, may keep water beneath the crust in a liquid state. If such an ocean exists, it raises fascinating questions about habitability. Wherever on Earth we find liquid water, we find life. Could the same be true beneath the ice of Triton? The faint pinkish hue of the surface suggests active chemistry, as sunlight breaks down methane particles and triggers complex reactions. This coloring, along with the smooth, relatively crater-free regions, supports the idea of recent resurfacing. Despite being one of the coldest objects in the solar system, with surface temperatures plunging near -230 Celsius, Triton appears very much alive in geological terms. Like a lonely wanderer, Triton's past carries the marks of a journey through a dynamic solar system, captured not just in gravity, but in ice and motion. Orbiting Neptune are also several smaller, irregular moons. Among them, Nereid stands out due to its highly elliptical orbit. Unlike circular paths that suggest formation near the planet, Nereid's stretched trajectory points again to capture. It may have been perturbed during the same chaotic period when Triton arrived, its orbit thrown into extremes by gravitational turmoil. Proteus is another of Neptune's moons, much closer in and far more regular. It is heavily cratered and roughly block-shaped, lacking the icy activity seen on Triton. Instead, it is a relic, a quiet reminder of the ancient solar system, undisturbed and frozen for eons. Smaller moons like Larissa and Despina orbit close to Neptune's ring system and are irregularly shaped, less worlds than captured rubble, maintaining precarious paths. These smaller moons do not rival Triton in size or activity, but together they form a fascinating contrast. Where Triton flows with frozen motion and hidden oceans, Nereid and Proteus cling to more static, silent roles. One may have been triggered into orbit by another's arrival. Together, they speak of the distant edges of the solar system, where gravity is both architect and storyteller, shaping icy bodies through encounters that span billions of years. In Triton, we see the echo of a solar system that refuses to settle quietly. Even out beyond Uranus, far from the warmth of the sun, frozen worlds continue to whisper secrets through orbits, eruptions, and silent revolutions. Far out beyond Neptune, at the edge of the solar system, lies a realm of ice and shadow. Here, where the sun is merely a bright star in the dark sky, the dwarf planets circle slowly in vast, elongated orbits. One of the most remarkable among them is Pluto, and orbiting Pluto is a moon so peculiar it redefines what we think of as a lunar system. Charon is not merely a satellite of Pluto. At more than half its diameter and roughly 1/8 its mass, Charon is Pluto's gravitational companion, locked in a unique celestial dance. The two bodies orbit a common center of mass, known as a barycenter, which lies outside Pluto itself. This mutual orbit makes Pluto and Charon a binary system, the only one of its kind among dwarf planets. Charon's surface is pale and scarred with fractures, evidence of ancient geological activity. One of the largest canyons in the solar system slices across its surface, a tectonic rift that may suggest a frozen ocean once flowed below. Unlike moons with dark, dusty exteriors, Charon reflects bright, icy light back into space. At its pole lies a strange reddish cap, a stain of chemicals formed from gases escaping Pluto's surface. These gases are captured by Charon's gravity, freeze upon impact, and are altered by energetic ultraviolet light from the sun. Orbiting further out from this binary pair are four much smaller worlds: Hydra, Nix, Kerberos, and Styx. Each of these moons has an irregular shape, formed not by slow accretion like Earth's moon, but likely from the debris of a long-ago collision. In fact, scientists believe Pluto and Charon themselves formed from a massive impact early in the history of the solar system, an echo of the mechanism that gave birth to Earth's moon. Hydra and Nix are brighter than expected for objects so cold and distant. Their surfaces, covered in clean water ice, reflect sunlight more efficiently than charcoal-dark asteroids. But these moons are small, tens of kilometers across, and their shapes are irregular. They tumble chaotically through space, their rotations unpredictable, due to the pull of Pluto and Charon's powerful tides. Kerberos and Styx are even smaller, darker, and more mysterious. Only the New Horizons spacecraft, passing through the system in July of 2015, revealed their presence and details. They are quiet sentinels on the edge, their surfaces bearing silent witness to the long history of this icy frontier. Beyond Pluto await other frozen worlds with stories of their own. Eris, slightly more massive than Pluto, lies farther still in the scattered disk, a region populated by icy bodies disturbed long ago by Neptune's migration. Eris also has a moon, Dysnomia. Named after a spirit of disorder, Dysnomia orbits at a far distance, suggesting a formation story that may involve capture or collision. Farther along the dark reaches orbits Haumea, an elongated dwarf planet spinning so rapidly that it's been stretched into the shape of a rugby ball. Its two moons, Naumaka and Hi'iaka, are icy and intriguing, orbiting a body that is itself a relic of some ancient cosmic collision. The moons appear to have been born from Haumea's surface, ejected into orbit by a violent impact billions of years ago. Their composition, rich in clean ice, hints at these violent beginnings. Even smaller trans-Neptunian systems are likely to hide similar secrets. A handful of other dwarf planets and Kuiper Belt objects, Makemake, Kwa, Gongon, have tiny moons of their own. Some moons orbit tightly, like watchful companions. Others drift lazily in elongated paths. Most of them remain faint blurs even in our most powerful telescopes. These distant systems, frozen and silent, remind us that the solar system is broad and filled with wonder. Out here where the light grows thin, gravity continues to sculpt moons from ancient ice. Each system, from Pluto and Charon's eternal waltz to the lonely arc of Eris and Dysnomia, invites us to see the solar system not as a place defined by the planets alone, but as a collection of stories, dances of light and motion, still unfolding beneath the stars.